Hello, this is the coding teacher, and I'm here to teach you how to code. Today I'll be talking about recursion. As always, this will be a no bullshit, no formulas approach to learning. I will focus on the practical aspects of recursion. I will give you a short explanation about recursion and tell you the two things or three things you always have to remember. Then I'll do a bunch of examples to help it set in. As always, my goal is for the video to be fast-paced and dense so that you don't get bored, and if you want to use it as a reference later, you don't fall asleep while watching. If you're just getting started with recursion though, you probably have to pause the video several times because I will go fast. I chose this topic because recursion is quite simple once it clicks, but it's actually, once it clicks, it's easy forever, but it's definitely hard to get it to where it clicks. It's hard to master. Recursion is simply a function that calls itself. Okay, it's a substitute for loops. So anything that you can do with recursion, you can do with loops and vice versa. So why do we need recursion then? If anything you can do with a loop, you can do with recursion and vice versa. Well, it's just the natural fit for some problems. So if you were to draw a fractal like this one, right? You see how there's a giant triangle, and then that one has an inverted smaller triangle there, and then that one is surrounded by three triangles. So like the recursion really starts from here, right? So you have this small triangle right here, this triangle in here, surrounded by three triangles. And each of those is surrounded by three triangles, if you notice. And then each of those is surrounded by three triangles. So if you want to do something that repeats itself, it is often okay to do it with loops, but sometimes just the recursive solution is way easier. So what is recursion? Again, just like loops, it's a way to repeat actions. Okay, most people will be familiar with this analogy of a right here of a where we say that a function is a black box, right? So it takes some input and then gives you back some output. Well, a recursive function is a function that calls itself. So what does that black box look like in this analogy? It's like this, right? So you call the function, then it reduces the input a little bit and it calls itself on a reduced input. That's why the box is smaller. And then what does that do? It reduces the input a little bit and calls itself on a reduced input again, right? Until it reaches some end condition. When it reaches some end condition, the smaller recursive call returns some output to the medium-sized recursive call, which returns some output to the bigger-sized recursive call, which returns some output to the original caller. Okay? So let's talk about the elements of recursion. So if you take nothing at all from this video, please take this. Memorize this, okay? Here are the elements of recursion. You're always going to have a base case. It's usually a simple if and a return statement, okay? So the base case is how do you solve, like, what is the easiest case of this problem that I'm being asked to solve? So if, you're counting, I don't know, multiplying numbers, or you're taking the factorial of a number, the base case is that the number that they gave you is 1, so you just return 1, right? Then the next two things is like you process some of the input. So you reduce the size of the original problem, and then you call the function itself. The function calls itself in a recursive call. So those are the elements of recursion. So let's look through some examples, right? So let's iterate through a string. The iterative, let's say that you have a string, whatever. The iterative approach to this is to, you could do something like this, right? For I in range from 0 to the length of the string, print the ith character of the string, right? So if you have whatever string, this would print the characters one by one, each in a new line. That's fine. That's the iterative approach to this. The recursive approach would be something like this. So if the length of the string is 0, just return, do nothing, right? Otherwise, print the first character. So that's what we're saying, right? About processing some of the input. Print the first character, and then here's my recursive call. Print characters recursively with the substring starting at character 1, right? So this shrinks the input. The original string might have been hello world. After this function runs one time, the first recursive call will be called with hello world without the H. And then the next recursive call will just be LLO world, just like low world, and so on. So we have a base case, we process some of the input, and a recursive call. So let's actually see that in action. Let me go ahead and pull up Let me get out of here and copy this and paste it right there. So then we're going to say print characters. Right? It just prints the characters one by one in each line. And now let's do it with this one. Print characters recursively. Same thing. Okay? So now next example is going to be a factorial. So our iterative approach to a factorial is to say, let's call product is n, right? For I in range 1 to n, this looks wrong to me. Product should be, oh no, yeah. So n, I could do it like this, right? Start at 1, and then the range, this range is non-inclusive of the last one, so range n plus 1, or start at n, so I already have it, and then range only from 1 to n non-inclusive. So I could do it either way. But what am I doing? Each number between 1 and n inclusive of n, I'm saying product is equal to the old product times the current number. So when this first product starts at 1, when this first run, I just do product equals 1 times 1. So product is 1, right? The second time it runs, I is 2. So I say product equals 1 times 2. So now product becomes 2, right? So this is my current value of product. So now I is 3. So what am I saying? Product equals product, which is 2, times 3. So my product becomes 6. So the next time that it runs, I is 4. So product is product, which was 6, times 4. So it's 24, and so on and so on and so on. So that's how we're going to get the factorial with the iterative approach. With the recursive approach, we can just say if n is less than or equal to 1, return 1, right? This will cover the case because the factorial of 0 is also 1. And then here we're just returning n, so this is my processing of some of the input, n times, this is my processing of some of the input, the result of the recursive factorial of n minus 1. So you see, we've broken down the problem. What is this going to evaluate to, right? So let's say that n was 5. What's that going to come out to? It's going to come out to n times the factorial of 4, right? Which comes out to what? 4 times the factorial of 3, which comes out to what? 3 times the factorial of 2, which comes out to what? 2 times the factorial of 1, which comes out to what? Just that's my base case, return 1, right? So that's how this result gets built. So let's go ahead and verify that this is the case. And then there you go, 5. You see? So that's another example of a problem that's solved with factorial. So then we have Fibonacci. Fibonacci is like the canonical example of recursion. It is not necessarily a useful thing in day-to-day life, but it comes up so often in discussions of recursion that you got to include it in an example. So the Fibonacci sequence is a sequence defined like such. You take a number, right? So let's say the Fibonacci number, what's the 10th Fibonacci number? So Fibonacci, it's a sequence, and the point of having a sequence is getting what's the sum of the the first 10 elements or the first 20 elements or whatever, or what is the nth elements. So this is how the Fibonacci sequence is defined. For the nth element, if n is 0, then the Fibonacci of 0 is 0. The 0th Fibonacci number is 0. If n is 1, then the first Fibonacci number is 1. For any other n, the nth Fibonacci number is simply the previous Fibonacci number plus the previous one to that one. Okay, so if you have if you want to know the 10th Fibonacci number, you have to add the 9th Fibonacci number plus the 8th Fibonacci number. Okay, so now let's look at two alternative implementations of Fibonacci: iterative and recursive. Right. So as you saw, like when you're defining the nth Fibonacci number, it is recursive already. Like this, even the verbal / mathematical definition of it is recursive because it references the same Fibonacci function in it, right? So the iterative approach, I'm not gonna go over it because it's relatively hard to explain. Well, I'm gonna gloss over it, right? You can pause the video and spend some time digesting it if you need to. So if number's zero, right, return zero. Else if number's one, return one. Those are my base cases, right? 0, 1. And then otherwise, you have these two numbers that are gonna be kind of like n1 and n2. So they're gonna represent these two, and you have to build up gradually until you get to the number that you wanted. Let's say that you wanted the 10th Fibonacci number, right? So you're gonna start. You already know the f of 0, f of 1. So you're starting from 2. Okay, so from 2 to 11, because again this is not inclusive in Python. So you have what's the current Fibonacci number? Fibonacci of 2 is the two previous Fibonacci numbers. So now adjust n1. So slide n2 is no longer the previous Fibonacci number. It's like two Fibonacci numbers ago, because now you have this one, right? So slide that one back. So n2 replaces whatever n1 was, and then f replaces whatever n2 was, and then you come back into the iteration. So now we're going to be looking for the third Fibonacci number, and again n1 and n2 represent the two previous Fibonacci numbers, and that keeps going on and on and on until you reach this guy right here, and then you return whatever f was in the end. I think that's pretty complicated, you know. Now let's look at the recursive approach. If n is less than or equal to 1, return n, right? Because my base case, so like for n1, the Fibonacci number is 1. For n0, Fibonacci number is 0. So if n is less than or equal to 1, return n. And we could add there, you know, some check to make sure it's not negative. And then simply one statement. Return Fibonacci recursive of n minus 1 plus Fibonacci recursive of n minus 2, right? Because what is this going to do? This is going to say, so let's say that you started out asking for the third Fibonacci number, right? So you wanted f of 3, right? What is that going to return? That's going to return f of 2 plus f of 1, right? What does f of 2 return? F of 2 is going to return f of 1 plus f of 0, right? So now all of these are base cases. So we have that f of 3 is simply going to be 2. You see? So the recursive call is going to keep calling itself and breaking itself down and converging towards the base case if it's correctly structured. But let's actually go ahead and test this code and make sure that I'm not lying. And then Fibonacci recursive of 3 should be 2, of 10 should be whatever it is, 55, and of 14, it grows super fast. It's a very fast growing sequence. So I hope that you can see that this, like if you understand recursion, this is way easier code than this, okay? And it's actually more intuitive too with respect to the definition of the function. So now let's go to a fourth example. Sequences, right? So what are sequences? It's a construct that you often use when you have like sequences of numbers. So for example, you have the sequence of 2, 4, 6, 8, 10, blah, 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 all the way to 200. What's the sum of that sequence, right? Or what's the nth number in that sequence? You can tackle both of these problems. I'm tackling the sum in here. So if you want to do the iterative approach to sequence sum, you can go ahead and it's relatively straightforward. You can go ahead and digest that on your own here, but you can see, you know, you're setting the current term, you're computing the n term, then what is my sum starts at 0, and then while current term is less than n term, you add the current term to the sum, and then you adjust the current term, move it up by the ratio 1, right? At the end, once you're done with that while loop, you return the sum. Not super hard, but not super easy either. With the recursive approach, we actually just have 2 steps. You know, my base case is if number of terms is 1, right? Just return the starting term. So the parameters that we have here, forgot to mention that, sorry, is the start term, the ratio. So how much does what's the difference between each term in the sequence, and then the number of terms. So we have the same parameters here. I just abbreviated them for space. So my starting term, right? If the number of terms in the sequence is 1, I just return my starting term. Otherwise, I return my starting term plus, now this is processing some of the input, plus my recursive call. Sequence sum recursive where do I start? Well, I already summed this one, so I start at sum plus ratio. And then pass the same ratio, and then how many terms do I have? Number of terms minus 1, right? So let's say that I wanted to find the sequence sum between the like for this sequence. For the sequence, just 1, 2, 3, right? So what would be my, I'm going to call this F for brevity, right? So what would be, if the sequence is 1, 2, 3, what would be my function right here? It would be F of start number is 1, ratio is 1, and number of terms is 3, right? And what does that evaluate to? Well, it evaluates to S, my starting term, 1, plus F of, actually, I'm going to do this over here. Sorry. Right. So what does that evaluate to? My starting term plus F of, let's look at it. My starting term plus my ratio, so in this case is 2. My ratio stays unchanged, and number of terms goes down to 2, right? So this is my original call. This is what it evaluates to. But what does this evaluate to, right? So let's take care of that. So that evaluates to 2 plus F of 3, right? So the next term, comma 1, comma, and then the length of the sequence is 1, right? And what does that evaluate to? So that evaluates to 3 plus F of 4, and that's my starting term. The ratio is still 1, and then the number of terms is 0, right? That's if I chose to structure it that way, but actually I chose to, I didn't have a recursive call at this point, right? So I could have chosen to structure it like this, and that's why I got confused, because I had it like that at first. And if I structure it like this, we see that it works. It's 1 plus this, which evaluates to this, which in terms evaluates to this, which in terms evaluates to 0, right? But so it's 1 plus 2 plus 3 plus 0, which is 1 plus 2 plus 3, which is what we were after. But in these alternative implementation, I'll actually recurse one fewer call if number of terms is 1. So when I get here, right, number of terms is 1, I don't do another recursive call. I simply return just the 3. I return my starting term. So in this implementation right here, this is how the recursive would go. Let's say we call f of 1 plus, we want to sum this sequence, 1, 2, 3. So we call f of start number is 1, ratio is 1, number of terms is 3. That evaluates to 1 plus f of 2, 1, 2. So my new starting number goes up by the ratio stays the same, number of terms goes down. What does that evaluate to? My new starting number from this call, right, which is 2 plus f of starting number goes up by 1, ratio stays the same, number of terms goes down by 1, and then when I come into this one, the number of terms is 1, so I just return the starting number. So this is there's no recursion here. So that just results in 1 plus this, but what is that? It's 2 plus this, and what is that? 3. So the 3, this recursive call evaluates to 3, right? And then this function call evaluates to 2 plus 3. So then I have my results. Okay, so another example, graph search. Okay, so let's say that you have a graph like this one, and this is how a short representation, right? You have a graph of friends, for example. So it starts with John, and then John is friends with Rob, Ned, and Arya. Rob is friends with Lord Umber. Ned is friends with Robert B. Arya is friends with the Hound and Brienne. And this is what that graph might look like in JSON, like if you were to represent it in JSON. So you have one object with two properties, name and friends. Friends is an array, right? And then each element of friends has the same shape. It's also the same type with name and friends, right? So this one is this first one is Rob Stark, right? Then Ned Stark, then Arya Stark, and if we expand that, let me fix this a little bit. If we expand that, we see that the friends of Rob Stark is another object with the same shape, name and friends, except we're not going to have any friends for Lauren Umber. And then we expand next Stark, same thing. Friends is an array of objects with the same shape, name and friends. And finally, we expand area Stark's friends, and we see it's an array of the same type of object with two properties, name and friends, and there's two in this one. So this is how you might represent a tree like this one in JSON. And so what if you want to, if you're given a tree like that, and you want to see if, the hound is anywhere in the tree, okay? So you would write an implementation like this one. Listen, I'm gonna go ahead and write it live. So let's say def find if friend in tree, and then let's go ahead and in here, what do I do? So what's my base case in here, right? If the first tree contains it, right? So like if I'm looking at this tree, right? And then later on, this function is going to be called on this tree and on this tree and on this other tree right here. So if the node that the root of the tree contains the value that I'm looking at, find a friend in tree, I need the tree and I need the friend also. Friend name. So if tree, if the object that represents the tree, the property name, if that is equal to friend name, return true. And then that's my base case. So now what I'm going to do? Well, for friend in tree friends, found in subtree is equal to, I'm gonna make a recursive call, find a friend in tree, passing the friend, because this is the subtree, right? And then friend name, right? So if, parentheses in Python, so if found in subtree, then I go ahead and return true. Otherwise, if I reach the end of this loop, right, and I've iterated through all the friends and I never found it, I'm just gonna return false from here. Okay, and I expect that this should work. Is complaining about indentation errors. Oh. Let me just save this as a Python file so that it gives me okay. There we go. All right, so now let me see if I can say Rob equals, and this should actually work, I think, even though that's JSON. Yeah, so let's say print Rob. There we go. So we have our Rob data structure, and now we're gonna call this same function, find friend in tree, where Rob is the friend tree, and then friend name is let's say Cersei. False, right? Now, who do I actually have? Oh, it was, oh my bad. This was Jon Snow, not Rob. But whatever, I misnamed the variable, the point still applies. So let's look for and see if we have Ned Stark. True. Let's see if we have Brienne of Tarth. That's also true. Let's see if we have Tywin. False, right? So, and you can see that because this is recursive, these friends structure could be like arbitrarily nested, and so long as your computer's memory can handle it, it will be able to search through and find, wherever it might be in the tree. So for this particular problem, you can see that the definition itself is recursive. You have this structure with name and friends, and then inside friends, there's other structures. This guy has name and friends, and this guy has name and friends, and inside those, them too, the friends of these also are structures with properties name and friends, and that can go on and on and on recursively. So if the definition of the problem is recursive, the solution will actually be easier if you do it recursively. In order to solve this particular problem without recursion, you need to employ either a stack or a queue data structure, and it gets pretty hard, to be honest with you. So hopefully that sheds some light on recursion. This is the coding teacher. I have nothing else for today. I hope that was informative. If it was, please like and subscribe, and I'll see you guys next time.